Okay, so for part 3 of homework 3-2 here, we had left off, we've talked a little bit about free body diagrams, although I might still come back to those just a touch more. And then the last thing that I left off on part 2 was I found out that the system was definitely going to be accelerating down the ramp because the 19.6, that was the force pulling down, and the static friction, which would be pulling up on that block, were not enough together to overcome the sine component of the force due to gravity pulling down the ramp. So I definitely know the system is going to move, and because of that, right, I know that static friction goes out the window. I do not care about that static frictional force anymore because once the system is in motion, I need my kinetic friction. So I'm going to do the same thing I just did, except I'm going to use my coefficient for kinetic friction, right? So again, using these same measurements, I've got 0.15, the kinetic coefficient, times 6 times 9.8 times cosine of 55. When I do that, I end up getting, and obviously this number should be a little bit less than the 8.4. So I end up getting about 5.06 newtons. So again, what that tells me then is looking at this block, right? I've got two blocks here. I've got the block that's hanging, which will be pulled upward, so that tells me the tension should be greater than the force due to gravity. And then I've got the block sliding down the ramp, which tells me that the sine component of gravity should be greater than both the tension and the kinetic friction that are resisting it, because I know that it is in fact sliding down the ramp. Okay, so that's helpful because in order to solve these problems, these are the problems where if I want to set it up, I have to set up an equation for the net force for each one of these. Okay, so again, this goes back to something we've done a lot of in your Physics 1 class, right, but we haven't seen as much of yet this year. So I'm going to set a net force up for each one of these. So I'm going to say the net force for object 1 and the net force for object 2. Well, the net force for object 1 would come from the fact that if it's moving upward, if the net force is going upward, then tension has to be greater than the force due to gravity. So if I've got a net force 1, then tension has to be, the way that I always described it, overcoming the force due to gravity, right? We know tension has to be bigger and gravity is working against it. So looking at that, I can break this up as the mass times acceleration equals tension minus mass times gravity. Well, the good news is I know the mass and I know the gravity. The bad news is I don't know either the acceleration or the tension. So that's where for this first part here I get stuck. But then if I do a second equation for my second object, the net force on object 2 would come from what? Well, the force that's going the same direction as the net force, right? Because I know the net force is going down the ramp because it's accelerating down the ramp. So the force that's providing that is my sine component of gravity. The two forces that are working against that sine component of gravity are tension and friction. And here it is important to note that this tension is, again, the same as that tension over there. So if I kind of break this up a little bit, again, I know this would be mass 2 times the acceleration. I've actually already calculated this. I found that this was 48.2, so I'm going to go ahead and plug that in here, right? Again, I don't know my tension, but I've already calculated my friction as well. My friction would be the 5.06 that we just found. So I've got those two measurements, and I also have my mass. So if I look at this system now, the only variables that I don't know are the acceleration of the system and the tension. Well, the good news is those are the same two variables for both of these equations. So I simply have a system of equations I have to set up and solve. So solving this the rest of the way out, again, I know the mass of the hanging block is 2. So 2a equals t minus, and then this number I already know. Again, I actually have solved that as 19.6. That's just the mass 2 times 9.8. And then over here I've got 6a equals 48.2 minus t minus 5.06. Now there's any number of ways that you could solve these using a system of equations. The way that I always recommend is take your two equations and simply add them together. Right? If I add the left side to the left side and the right side to the right side, I'm still keeping the equations balanced, but I'm doing so in a way that eliminates the variable of t. Right? So again, if I take this and I add to it 6a equals the 48.2 minus t minus 5.06, I'm just adding these two sides. Well, on the left-hand side, obviously, I just end up with 8a. On the right-hand side, the perfect part about this is I end up canceling out the t's. So my tension actually drops out of this equation. So 48.2 And then I have two negatives, minus 19.6, minus 5.06. So the only variable I have here then is my acceleration, right? So I have 8 times the acceleration equals this whole mess over here. When I calculate that, I get that to be about 23.54. And then dividing both sides by 8, I get my acceleration to be 2.04. So now I've got my acceleration. The question actually asked me, though, for part B, it asked me to find the tension, right? So once I have my acceleration, how can I find my tension? Well, not too bad, right? All I have to do then is take this acceleration and plug it into either this equation or this equation. And in fact, if you want to double check your answer, you could plug it into both equations and make sure it works out correctly for both. I'm just going to use this equation down here because that's actually the easier one to work with. So 2 times the acceleration of 2.04 equals t minus 19.6, and then solve for t. Well, if I solve for t, I end up getting, again, about 25.5 once I actually solve that. Okay, so I end up with about 25.5. But anyway, so I've got that set up, I've solved that out, and I go from there. So I've got my tension. If I wanted to double check, again, all I have to do then is plug in my and I'm sorry, this was not 2.04, this was 2.94. That makes more sense. This was a 2.94. Anyway, if I take that and I plug that into this equation as well, I should solve for that t to be about the same thing. So anyway, I've got part B, I've got that answered. So then part C asks me how fast, what is the speed of the object after 2 seconds? Well, that's just going back to kinematics, right? We know that both blocks are moving with the exact same acceleration. So this one's accelerating down the ramp at 2.94 meters per second. This one's accelerating upward at 2.94 meters per second. Both of them started at rest. Both of them have been traveling for 2 seconds because that's the time that it's asking me to find it at. And again, I know the acceleration is 2.94. So this really is just a simple kinematics equation for part C. Right, if I want to find the final velocity, the final speed after 2 seconds, I'm just using my velocity as a function of time. So I'm finding my final velocity, my initial 0, my acceleration is 2.94, and my time of 2 seconds. So finding that final velocity, that's where I got my 5.88 meters per second. And since the question actually just asked for the speed and not for the velocity, I'm not worried about any direction. And in fact, I know both of these blocks are moving at that same speed because the system's not getting closer together and it's not falling further apart. So I've got that number to work with. So then just to recap a little bit here with the free body diagram, since I do know the information, I should try to be specific. Okay, the biggest thing that I would look at here is what can I do about particularly object 1 and the tension, right? So going back to this, I actually know, again, because the system is moving upward, I know that the tension had better be bigger than the force due to gravity. So if I was actually drawing this free body diagram and knew that information, I should make it reflect that information. So again, the tension is greater than the force due to gravity. In terms of this, there's not a whole lot we have to worry about. However, I know that the sine component of gravity would be more than these two forces, so I'm actually going to make my force due to gravity significantly bigger than either my friction or my tensional force pulling up. Because again, I know that just the sine component of that force due to gravity has to be bigger than this, so of course the hypotenuse is going to have to be significantly bigger than either of those two. Right, so if I was doing my free body diagram with the information that I now know, it'd be these two blue diagrams, which would be slightly better reflections than the two that I had drawn in black earlier. But anyway, make sure you're thinking about those things as you draw your free body diagrams.